team did was to extend this to the entire distributions, like a so-called density function or the CDF that we looked at before in the first slide. You don't even need the hazard functions. But if you have selective influence at the level of your cumulative distribution functions, then you can identify all these different architectures and the stopping point at the same time. So notice, and this is really the key thing, like, can you go back to the, yeah, thank you. So notice that these very unique signatures, like if you have this first go up and then down to negative, no, that's not it. This is the exact predicted signature. It's completely parameter free and distribution free. Any system that's serial and is exhaustive, i.e. does both items for whatever the two tasks are, subtasks or whatever, has to look like this. If it's parallel and an and or exhaustive, it has to look like that. It's all negative. If it's a race of some kind, that is, you can stop as soon as the first one's done. If it's serial, it's identically, this is not just a point, this is a function. It's identically zero for all times. And we should have pointed out more that this is the time axis here. And this is the so-called survivor interaction contrast. It's the extension of what Sternberg used on the means to the entire distribution. And the survivor function is just one minus that cumulative so-called OGI later, probably hopefully in statistics. So the race model, or the first terminating minimum time, is always positive for a parallel model and identically zero for a serial model. Here's the notion, the other thing, nice thing that SFT does is give you workload capacity. So by varying, in the so-called double factorial paradigm, we'll see in a moment, by varying both the number of tasks or subtasks you have to do, that allows you to study the capacity, workload capacity, and varying brightness or some other kind of salience allows you to get those SIC functions and get the architecture. So quite a powerful thing. Here's a concept of capacity, limited capacity, in that if you have a single item here, and then you go to two, maybe you have to divide up your resources, or there's inhibition or something that produces limited capacity. Unlimited means it's parallel, and each channel has exactly the same speed and efficiency as when there's just one thing. And finally, supercapacity, which would be very unusual to just be able to produce more energy like that, but Daniel Kahneman in his early work in vision suggested that might be true. I've never seen the evidence of it. But more likely is that you have a Gestalt configural system where these guys interact in a positive way and produce a Gestalt, and that can yield, in many of our experiments have shown that can produce supercapacity. A lot of equations, so we've got, I'm not going to go through these obviously, but we've got equations that produce entire functions for what happens if you do have supercapacity or not. This guy in the N case, where you have to do both things, your case, either one does the trick. So this C of T is less than one limited, and these are entire functions, remember, again, minus the number. The function is at 1, always, or it's bigger than 1, gives you supercapacity. Supercapacity, and of course what we see here, since this is a dynamic function, sometimes you get supercapacity early on at the faster times, but limited capacity things somehow inhibit one another. How much to put in? Anything? I should have asked probably 2 minutes? 10. I'm rich. So a summary is SFT measures based on response time. You can identify mental architecture, the stopping rule, workload capacity, but it's not good for what GRT can do most naturally is to test different things. here is the original one that Georgie Nazawa and I worked out, and back in the days of the late 80s, early 90s, believe it or not, everything was still serial. Everybody thought reading was entirely serial, and memory search was serial, and on and on. So what we wanted to do was give the utmost opportunity for things to be parallel. And our thinking was, well, what could be possibly more parallel than the two dots presented to the two eyes? Okay, so that's why this is so preternaturally simple. So this was a war experiment, like probably 150 or 200 experiments have been done since then, are or. You have many, many fewer and experiments, but they're just as good, in some cases better. Sometimes, even if you give a person a Gestalt kind of object, they'll still, if they can, process just a single feature to make the response. And they can do that in an or experiment. But if you give them an and experiment where they have to do both, then they'll often show Gestalt characteristics in supercapacity. So here's a more advanced notion, and especially used by Mario Fivich for categorization kinds of things. So here's the category in the upper quadrant there are yes responses, or ask for yes, and these are no responses. And I'll go into the stopping rule for all of them, but the stopping rule up here is an and. Okay, you have to process both dimensions. This will be the fastest. Notice it's farthest away from the no stimuli. And these guys are intermediate here, and that one is the slowest. And that's being used now. It's almost taken over the field. It's quite popular. It was first used by Mario in his thesis. Now, selective influence is what my other talk was, but was fairly more technical. So I'm not going into that very much, but it's the critical thing underneath. And Sternberg also recognized this. But he asked only for selective influence that these factors would affect the means of the two sub-processes. And we showed that you need more than that. You need an ordering or selective influence, again, at the level of the distribution. Remember I told you that these are the survivor functions. Survivor, the name that came out in, actuarial stuff has been used since at least the 1800s, some going back to the 1700s. So a survivor is, for example, probability that you've survived this long, say at age 80, and after that, you go down fast, or maybe some people have cancer or something and die up earlier, but it's 1 minus the cumulative distribution function. So notice the nice ordering here. This is selective influence operating. So perhaps let's go back to color and shape. You have lesser noise and a brighter color gives you the high. Oh, I'm sorry, this is the slowest because it's a probability that you get done given you're not done yet. And this is the slowest. This is the fastest because the probability goes down that you're not done yet. Faster, right? Sorry about that. So this is the high, low, and low. If you have that order, you can do all those tests that I mentioned. If you don't, sorry, Charlie. Now you still might be able to do different tests for the capacity, and vice versa. So you don't have to do a shift completely, but you would really like to get this selective influence. Again, those are the things we've already seen how it works. Oh, sorry, that was the word. Funny. Yeah, no, this is okay. Right. No architecture, however, workload capacity. And these are just examples if you don't have time for. It's very interesting to study what happens to selective influence when, for example, suppose it's serial and the time it takes for your second sub-process, like maybe here's visual perception and here's doing a mental arithmetic test, like adding two numbers or something. Well, if the time you take to perceive affects the time to do the task, then that's a failure of selective influence at a micro level, but it might not contaminate the marginal level. It could be averaged out. Well, that's some of our newest results. I'm very fascinated on that, but we won't be able to do it today. But I'll give you a teaser, okay, so that maybe you want to see what the results later. And this actually is again June's thesis, my co-author here. I won't be able to spend time on this, but it's applying these methods to a situation where you have a categorization. So the prototypical thing is maybe you're running a 7-Eleven store and somebody comes in and they're dressed like a gang member, okay? Or they're dressed with a nice suit and tie like you guys today, right? Well, you make a categorization of I think it's a gang member, I think it's not a gang member, and then you either take an action, say you call the police or grab your gun, or you give them a free candy bar, right? Depending on, to some extent, how you categorize them. Now, almost all models that try to get quantitative psychology for perception, cognition, are Markov. They're not independent, so surely, as you would expect, your response or action, aggressive or not, depends on how you categorize. If it's fully Markov, your final response will no longer depend upon what the stimulus even was. Does that work? No. There's an interaction so that you still have some influence of the original stimulus. Even if you say he's a gang member, you don't act like, which in some, and we can show this, optimally you should. You should say, always take an aggressive action if you think it's a gang member. That doesn't happen. And that kind of, I said, a very unprepossessing, some might want me to contribute to a very strange journey. And so this was buried for about 20, 30 years until my colleague, Will Busmeyer, brought in his quantum theory of decision-making, and his quantum theory predicts the kind of interaction that we find that fails the Markov test. Almost done. So I'm not going to go through all this. I'll have to, don't tell Andrew I didn't go through all this. So yeah, she's using SFT analysis of this. And there is some parallelism, even though the stimuli are presented in a sequential fashion, there is some parallelism. I can't really say much more than that right now, unfortunately. And that's it. Thank you very much. Ha ha, I did it.
Thank you for James' talk. So, does anyone have questions?
So what is your plan for next steps of your work and your work with the
Well, yeah, June, of course, as you're taking postdoctoral, you have to focus on what they're doing. Okay? But what we're going to do, is ongoing right now, is to bring, thank you for asking the question, is to bring in the two branches into a unified methodology. So what we have done very recently, in the last 2 or 3 years, we've had the same subjects in the same kinds of stimuli, but doing block of GRT, then block of SFT. But we want more than that. We want to an experimental design that has both of these guys on every trial. So the same trial information allows you to do the test for SFT as well as GRT. And we've got some early pilot data on that with a brilliant new design that Michael Winger, my colleague there, has. Okay, thank you. Thanks for that question.
Gina, I do have some questions for you. So, according to testing GRT and SFT, according to these two frameworks, how do you define computer perception? Because this meeting is TNC here. Actually, this meeting is named after my gene, and we have a very nice study called CPC
understand your question, and that's a question as I would expect. What we think is the most likely scenario of a system that obeys high configurality would be that, oddly enough, usually the most efficient kind of search, if it's sufficient to give you high accuracy, the payoff would be self-terminating process. So you only process as many features or whatever as you need. However, if it's truly gestalt and molded into a single thing, that will show up as exhaustive processing. So it's kind of anti-intuitive and therefore makes a very strong prediction. Okay. It would also be high in the GRT perspective. It would be a high positive correlation among the features or the dimensions. Okay, and super capacity. That's. Thank you. Yes, sir.
Okay, nowadays there are some technologies for machine learning, for instance, the support vector machine. When they do categorization quite well, but they don't have any assumption about probability distribution of information. So how?
I'm sorry, we're talking within GRT or SFT or?
GRT, for instance.
GRT.
All right. So for GRT, you have to make assumptions about the probability distribution of the condition, right? So you have to make some.
You can. So we do the non-parametric test. At least I encourage everybody to do the non-parametric test where you don't have to know the distribution. They have to be probability distribution, but you don't have to say.
But you have the probability distribution.
Yeah, you assume their probability.
Yes.
Absolutely.
Yeah, but nowadays, for instance, some technology like the support vector machine, they don't need to make this assumption. All they are dealing with the distance between the machine function, right? So I just curious how you guys, is there any possible way to combine this approach?
So what was the second approach?
Support vector machine, for instance.
Well, yeah, there are 1,000 different decision rules you could use, and they have them too. And all I can say is that you look at each assumption or machine or even like a distance kind of concept, and it'll make predictions about what these various statistics look like. And will they be true? I don't know. We have to test. Thank you.
Thank you, Jim. It was a great talk. I like to throw in a slight different aspect because our perceptual system actually changed with our lifespan. So when you were a baby, you cannot see very well, but when you become older, the perception declines. So I know the work you're doing is already very complex, trying to bring two big models together. But I really want to throw in another more complex issue. So how should we configure the developmental change in your models? So what will be the parts? Of course, there will be several. I think that the capacity will be different, architecture will be different, but when in real life, we do have to deal with the
Right.
okay. So that's my
Good
question.
question. And by the way, I meant to, in my introductory remarks, I meant to especially commend Jing Ta and his group on bringing these very scientific things, which ordinarily usually stay in a rarefied atmosphere of psychophysics or something like, and apply to some of the most important problems in medicine and health. Really important applied things. I think the research, for example, in aging is just getting started. And a little bit is done with Jing Ta and by other people using SFT, very, very little of GRT, and I think it has a role to play on the interaction of dimensions as you age and things like that. So I think it's got a lot of promise, but there's not much there yet. One quick result that has been found with the aging and SFT is that, and of course we have to specify the experiment, because if you change the task, maybe it changes. But in this task, it turned out that indeed younger people had more corrects in accuracy and were faster. But if you looked at our capacity measure, they actually suffered, younger people suffered more when you increased the workload than the older people did. So this is the kind of thing that's extremely important to what's going on and how you medicate it or, let them meditate or whatever. So I think it's got very much promise, but again, it's very early stages.
Thank you.
All right, thanks, Jim.
Oh, I want my certificate.
Upside down. Upside down.
Oh, beautiful. I'll put it in the front.
Thank you very much, Professor James, for the wonderful lectures. And next, we will invite Professor James Townsend from National Taiwan University to share his research findings. And let's welcome Professor Hui Lin-Jian. Hui Lin-Jian to briefly introduce Professor Chen.
I wonder if it's okay just not use the microphone. Is it clear enough? Okay, cool. So good morning, everyone. It's a great pleasure to introduce Dr. James Townsend, aka CCC or Triple C, as my former postdoc mentor, but also a lifelong friend. So I'm thrilled to share his expertise and achievement with you all today. Jian Zhong received his PhD from UC Santa Barbara and had several postdoc training. Dr. Jian Zhong, I think he has exceptional talents in mastering critical tools in visual and quantum neuroscience, such as psychophysics, mathematical models, functional brain imaging, and visual evoked potentials. And he has also published numerous papers exploring the neural mechanism and mathematical models of spatial vision and color vision. And Dr. Chen's groundbreaking work has been honored with many high-profile awards, so including Young Investigator Award by OSA, Mudayo Memorial Award, and Distinguished Research Award by NSTC. So today, he will invite us with the divisive inhibition as a solution to the correspondence problem in perceptual belief. So please join me in welcoming Dr. Chen.
You guys just heard James talk. Right? Actually, that brought a lot of memory for me. The first time I encountered the name of Townsend and Ashby, when I was an undergraduate.
That made me sound too old.
The book of Ashby Townsend was one of me. So that's the first time I know his name. And a few years later, I went to the University of California in Santa Barbara. And Ashby actually sat in my PhD meeting. So I actually read quite a bit about general incarnation mark theory about him. Okay, and I actually published a couple of papers on using GRT. Okay, so in a sense, I kind of very remote cousin of James' academic family. Okay, but here today I'm going to take a very different approach. The reason here is that I start with neural data on intellectual physiology. You have one property, which we call the undivided principle. That is, no matter how many dimensions there are in your inputs, there always one dimension, namely impulse per second. Okay, so that's reduce everything into one dimension. The second property of neuron is that neuron is highly nonlinear. Right. So most of my work is trying to deal with this kind of nonlinearity, rather than probability. Okay, so that's the reason why it's kind of similar problem. No, we have how the visual system put one and two together. But the thing is that we take a quite different approach. Right. So here today I'm going to talk about three things. One is divisive division. Try to characterize the neural nonlinearity. Find the corresponding problem. Why is it a corresponding problem? Because when you do perceptual grouping, you have to link random image features together. But in the meantime, you actually remove unwanted connection. Okay, that's the purpose. Okay. really good at combining major things together. For instance, here, for the first time, actually I tried that in my class. If the people first time see these things, it's very difficult for them to figure out what's going on here. Of course, there's a dog here. Now, of course, you two you know what's going on. Okay, very hard here. But actually, if you don't know what's going on here, it's just a function of black dust, right? And also here you can see this kind of you see a circle, right, on a bunch of black dust. So the idea of preserved grouping is that all visual systems have to combine individual image elements into a coherent object. Okay, and to do that, configuration is important. Okay, here is an example. Here you can see a circle here. Here is nothing, right? But actually, if you look carefully, you can see the pattern on the two sides are exactly the same. Even the noise are the same because I created. I just moved the circle, the element of the circle around. Okay. Now, even though you can remember, okay, here's a circle here. Okay. Now, even remember that. You still have no idea where they are. Okay. So configuration is important. Okay. And then observation is also important. Here is an example. For instance, this is a typical, this is a kind of a typical case in spatial vision. You have a vertical grating and a horizontal grating. If you vertical pass, for example, you get this kind of pattern, right? But if you move pattern together, you get a checkable pattern whose orientation is 45 and 135 degrees. There, the vertical and horizontal. Okay, so operation is important. Okay, okay. Preserved grouping has been studied for like a century. You know, this is actually kind of a central in the Gestalt psychology. Okay, but it's actually that Gestalt you bring the Gestalt, you know, there's 6 fundamental Gestalt rules. But actually, over the years, there are many Gestalt rules proposed every couple of years. Okay, even now, even today, there are new rules all the time. Okay. So there are laws for that, but this law cannot explain much of the preserved grouping. One thing here is that sometimes there are kind of ambiguous situation here. For instance, in figure A, you can see 2 symmetric patterns, right? Symmetry is very important. This is one fundamental Gestalt law. And then, but you put them together, you don't notice the symmetry. You actually see this kind of contour here. Of course, you can say, well, that's good continuity so far. But then how about next one? Symmetry. But here again, the symmetry disappeared. And notice that there's not even good continuity 6. Okay, so this kind of group is a kind of tree. You have no idea what's going on here. Okay, so there is no approach of which role should be used. And also, it's also occurring in the real case. What do you see here? A girl, can be a guy? But actually, it's a guy, can be a girl.
Yeah.
Okay. So my idea is that actually there's two Gestalt roles you work here, right? One is this guy. This is the side of a guy. This is the side of a girl. Okay. 2 good continuity roles. Okay. And but you choose one of them, not the other. Why? Okay. So we try to understand this kind of phenomena. I start with role detection or latent detection. So for instance, here the task is to detect target in the presence of a flankers. Okay. And typical result is that the central way goes down and goes up. That shows that the flankers actually can facilitate the detection of the central target. This is very good because we tried, this is the first step of Gestalt, because we have to link objects together. Okay. And my first start is actually a single cell recording. Okay. And we record the LS17 neuron. Okay. With the target. And we make sure that the context is outside the field. Okay. So idea. So if you present a single target, the neural response, okay, going like this. This is a contrast increase, but the response going like a sigmoid function of contrast. Okay, that's a kind of